In this video, I'm going to talk about the logarithmic function. Now, logs were originally used to try and do large-scale multiplications really easily because somebody figured out, like, oh, it's a lot easier to add than it is to multiply. So that's where these kind of log tables came up. And the log function is basically just like an equivalent or almost inverse form of the exponential function. So if I have, let's say, a as my base to some exponent x, and that is equal to b. So that's a general kind of exponential form. The logarithmic form of that would be log a, because that's my base, b is equal to x. So the log of base a with b is equal to x. And we can see it's kind of like this kind of equivalent kind of function between the exponential form and now the logarithmic form. So for example, if I have 3 to the 4 is equal to 81, the logarithmic form of that would be log of 3, 81 equal to 4. So just kind of rearranges it. So logs are kind of useful, and they actually help us to, in this case, to kind of solve values of x for exponential forms. And logs have their own kind of properties and laws. So if I take a look at one of the basic properties of a log, it is that the log of a1 is equal to 0. And this all flows from, no matter what, if I have any base to the exponent 0, it's going to be equal to 1. So this is kind of a fundamental property. Second of all, if I have log of a, and now the a to the x. So now I have my base and my answer equal to, both are the same, but it's also raised to the exponent x. Well, this will just be equal to x. So it's only equal just to this exponent. Now there's proofs involved with this, but I don't have enough time to go through them now, but you can look them up online. And the last kind of property would be if I had a to the log, now we have a logarithm as an exponent, a to the x, well that's just also equal to x. Now one of the things I also want to point out is if I have any sort of, let's say, logarithm, let's say log 10, and then I got 10 to the 4, well that's just going to be equal to 4 log 10 to the 10, which is equal to 1. Whenever you have these kind of exponents here within the logarithm, they merely just move to the front. We can move them to the front, so it would be 4 times log 10 of 10. So that's a very important kind of little trick, is this moving of an exponent within the logarithm to the front. And that actually helps take care of a lot of issues and questions we can see a little later on. Now, one of the first laws of logs is the product law. So if I have log a m times n, well that's going to be equal to log, still a, m plus log a of n. So whenever we have like an addition between logs, as long as they have the same base, then we can just kind of multiply these coefficients together. So we can just kind of multiply those things together. So that's actually a very, very handy thing. So if I have, let's say for example, log 6, 4 plus log 6 to the 9, well, that's just going to be equal to log 6, and then we have 4 times 9, which is equal to log 6, 36, and that is equal to 2, because 6 to the power 2 is equal to 36. So that's pretty handy. Now, for this one, it's actually fairly easy for me to find out the answer, because it was like, oh, okay, 6 to the power 2 is 36. It's fairly obvious. But there's actually a trick we can do in our calculators to figure out what the logs are. Because all of our calculators basically have just log base 10. And there's obviously millions and billions and infinite number of other possible logs. But we can use that log base 10 to figure it out. So if I take this one, here I'll extend it down. If I take this log 636, and in my calculator, I put log, and it will be, if it's blank, it's automatically base 10, 36, in brackets, divided by log base 10 again, 6, that will equal 2. So if you have just log in your calculator, you can just kind of like split this up into kind of division, which is essentially log 36 over log 6. And that's how we can calculate it using our calculators, just directly, if we get something more difficult than this. Now, moving on, we have our quotient law. Oh, spell that correctly. Our quotient law, and it is if I have log a m over n, that's going to be equal to log a m subtract log a of n. So in this case, with the quotient law, we just have division, but then we just have a subtraction of the two logarithmic functions. So if we have, let's say, log 2, 72 minus log 2, oh, my bad, not log 2, log 6. Log 6 minus log 2, so that's just going to be equal to log 6, 72 divided by 2, which is equal to log 6, 36, which we now know is 2. So, quotient law, when it's divided, we have a negative sign, or if we have one log to subtract another one, we can go backwards and make it a division. All right. One more law we have is the power of a power, and I've kind of already gone over this one. So if we have log a m to the n, it's the power of the power law, it's going to be equal to n log a m. So, like I said before, this just kind of moves here, which is actually super, super handy for these types of questions. So, if we have, let's say, I don't know, log 8, and we have 9 to the 2, well, that's just going to be equal to 2 log 8 to the power 9. So all this exponent does is just kind of moves to the front of the log and becomes a multiplication. And that's all this really power of a power. Power of a power law these are three very like key laws for solving logarithms. So now let's take a look at, I don't know, just like solving algebraically for these logarithms. So let's say if I have, let's start with something a little easy. Let's go log x 9 is equal to 2 over 3. Now here I can just use kind of my exponential function and kind of work backwards. So I have x as my base, and 2 over 3 is the exponent, and that's equal to 9. So once I have this, then I can just kind of do the reverse. I can just like go to the power of 3 over 2 and power 3 over 2. So this, when the exponents are multiplied through, is 6 over 6, which is 1. And then we have 9, 3 over 2. So we have x is equal to 9, 3 over 2 is 27. So that's one way to do it when we have like kind of x as our base. Now, another type of question is, say, something like this. I'll do it right over here is log 2 30 x. So now my variable is within the log function, and now I have minus log 2 5 is equal to log 2 12. Alright, so now I have a whole bunch of things. So first thing is I'm going to use my quotient law here, and I'm going to go log 2 30x over 5 is equal to log 2 12. Now, I have log 2 here and log 2 here. That means that this part of my equation and this part of my equation have to be equal. So that means 30x over 5 is equal to 12. So 5 times 12 is 60, 30x, 60, 30, 30x is equal to 2. Now, let's take a look at one more example. Let's take a look at this. Log 7 x plus 1 plus log 7x minus 5, and that's going to be equal to 1. So use my product rule right away. If you see an addition or subtraction, you're going to use your quotient law or you're going to use your product law. So here, addition, product law. So now I have log 7 x plus 1 x minus 5. So now I have this kind of quadratic in here. And this is all equal to 1. So I'm just going to multiply through my quadratic. So I get log 7 and I get x squared minus 4x minus 5. And that's equal to 1. Now, what do I do about this 1? So it's not log 7 1. I can't like equate this to the 1. But since I have a base 7, I can go back and use the exponential form to solve it. So I know that this 7 to the power 1 will be equal to x squared minus 4x minus 5. So 7 to 1, so I bring it over. 0 is equal to x squared minus 4x minus 5 minus 7. 0 is equal to x squared minus 4x minus 12. But we want to know what x equals. So to figure out what x equals, I'm going to have to factor it. So I factor it and I get x. So this is 3, 1, so 6 minus 6, x plus 2. So in the end, x will be equal to 6 and negative 2. So combining a lot of things like factoring, using our product laws and using the quotient law, and then getting it here. So logarithms are super useful, especially when we're dealing with exponential questions and solving different functions that way. And it just gives us another tool to use in our toolkit for mathematics.